Here we go again. This time we're going to be looking at the normal approximation to the Poisson distribution. Voila. Okay, here again we're converting from a discrete distribution from the discrete domain to the continuous domain, from a PDF of a discrete random variable to the PDF of a continuous random variable. And of course, continuity correction is required. Now, what's the condition that must be met for you to get good approximations if you want to convert from the Poisson distribution to the normal distribution? Well, lambda must be greater than 15. Right? The statisticians / mathematicians that be, they worked all that stuff out. We just have to use the value that they gave us. Once lambda is greater than 15, you're allowed to convert a Poisson distribution into a normal distribution. That is, you're allowed to get the normal approximation to the Poisson, and the probabilities that you can calculate from that will be very good approximations. All right, and that's pretty much it. If x is Poisson lambda, and you use the normal approximation, x becomes normal. And the parameters are lambda, lambda. Lambda is the mean, lambda is the variance. There's not much more theory associated with it, so we're going to just jump right into a couple of problems and work our way through. Here we go. First problem. The number of eggs laid by an insect. A second. Yes, the number of eggs laid by an insect follows a Poisson distribution with parameter 200. And then they ask to find certain probabilities. Well, the first thing we're going to do is we're going to describe a random variable. X is a discrete random variable that represents the number of eggs laid by an insect. And they told us that it follows a Poisson distribution with an average value of 200, right? It's a Poisson distribution with parameter 200. So they're telling us that lambda is 200, and therefore x follows a Poisson distribution. Oops, what happened there? X follows the Poisson distribution with parameter 200. We can use the normal approximation to the Poisson because clearly lambda is way more than 15. So you can just jump right into that. If we use the normal approximation, we end up with x now being normal, 200, 200, lambda, lambda. And then based on that, we're going to try to find the probability that more than 170 eggs are laid. So starting with the probability that x is greater than 170, we're going to apply continuity correction. That'd be nice if I can fix that. There we go. Yes, if we apply continuity correction, not sure what's going on here. My letters are changing into other things. My God. Okay. Continuity correction will give me the probability that x is greater than, well, by now you should get the hang of this. Greater than 170, you don't want to include the 170. So you start at 170.5 and greater. That would not include the 170. If we standardize that, this becomes the probability that Z is greater than 170.5 minus the mean of 200 divided by the standard deviation of the root of 200. This becomes the probability that Z is greater than and divide by minus 2.086. Okay. We're gonna sketch our standardized normal distribution graph. Well, yes, the standard normal distribution minus 2.086 somewhere over here. And we're talking greater than that. So we're looking at this portion of area right there. If you flip that graph, that becomes a probability that Z is less than a positive 2.086, which is phi of 2.086. And lookup table should give us that number, 2.08. .9812. Six. When you get to 6, let's add 3 plus 0.0003. So we're looking at probability that X is greater than 170 to be approximately 0.9815. There. 0.9815, that looks good. The second part is more than 205 eggs are laid, more than 205 eggs are laid. Looking for the probability that X is greater than 205. Greater than 205. Again, you have to apply continuity correction. Continuity correction gives me the probability that X is greater than 205.5. I want to exceed 205. Standardized, this becomes the probability that Z is greater than 205.5. Minus the mean. The mean was what, 200 again, yes? Divided by the root of 200. This becomes the probability that Z is greater than 5.5 divided by 200 divided by the root of 200. It'll give me 0.389. That's a positive 0.389. Okay. All right. If I graph this, what am I looking at? 0.389, somewhere over here. And I'm looking to shade that region. And this is clearly, by now, we should be experts at this. 1 minus phi, or 0.389. 1 minus 0.38 is 0.6480. Looks like, and 0.38 and then 9. 34, it looks says there. Not 34, 0.0034. Let's see what this gives us. Two 0.3486. And this represents the probability that x is greater than 205. Okay, how do you like them apples? This is pretty decent. Okay, next. We're looking at finding the probability that, between between 180 and 240 inclusive. Between 180 and 240. Okay, because looking for the probability that x is greater than or equal to how could I forget that? 180 and 240. And 240 inclusive. So we'll simply go 0.5 less than 180 and 0.5 more than 240. Right? Under continuity correction. Boy, gotta end up doing all this formatting, man. What's wrong with you? Yes, under continuity correction, we're looking at the probability that x is greater than or equal to 179.5, less than or equal to 240.5. 180 and 240. Good. All right, so what am I going to do? Standardize. This becomes the probability that 179.5 minus 200 under root of 200 less than or equal to z less than or equal to 240.5 minus mu 200 over the root of 200. Let's see if I can get those z values. One point four 1.450, and on the other side, that should be a minus 2. Yes, this should have been negative. Yes, over on the other side, we're looking at 2.864. Sketch. What are you looking at? Minus 1 point something, minus 1.450, and positive 2.864. Looking for that region right there. Man, we should be experts at this normal distribution thing by now. Okay, so what are we looking at? Probability that Z is less than 2.864 minus the probability that Z is less than minus 1.450. Phi of 2.864 minus into 1 minus phi of 1.450. Phi 2.864 plus phi 1.450 minus 1. Oh boy, this lookup table thingy. 2.864 2.8 2.86.9979 plus and 4. Just add nothing. 1.450 0.9265 minus 1 point, that's the 1.45 0.93, no, 265. And 0. Nothing else after that. Okay, so therefore, we're looking at the probability that x is between 1/8 and 2/4 inclusive is approximately equal to, oh, forgot my minus 1. Zero 0.9244. Zero 0.9244. There. 0.9244. That looks good. Okay, the last part is the probability that an egg develops is 0.1. Show that the number of survivors follows the Poisson distribution with parameter 20. So now we're looking at the number of eggs that develop, or the number of survivors. Number of eggs that develop is equivalent to the number of survivors. The probability that any one egg develops is equal to, forgot the value they gave, is 0.1. X will be the number of survivors and if we have a p-value of 0.1 and an n value of 200, Now we did an average 200 eggs that are laid. Then X is number of survivors out of 200. And you can clearly see this looks binomial-ish. Probability that any one egg survives is 0.1. And out of 200 eggs, X is binomial 200 and 0.1. Yeah, this is taking me into binomial. They kind of jumped the gun on this one, or maybe not, because in the text this part came before. Yes, technically this is binomial to Poisson, right? Where give me a second, let me gather my thoughts here. This is the Poisson approximation, and X becomes Poisson lambda, where lambda is equal to NP. N is 200 and P is 0.1. The conditions for converting from binomial to Poisson is that N must be greater than 50 and P must be less than 0.1. Well, P is exactly 0.1, but I'm not going to split hairs on that. N is quite large, 200. So therefore, 200 by 0.1, that's 20. And therefore, we can use now X as being Poisson 20. I'm converting from a discrete distribution to another discrete distribution. I don't need continuity correction. Somebody riding around at this hour in the morning. Good. So I just showed that the distribution that represents the number of survivors can be modeled using a Poisson distribution with parameter 20, and based on that, what do they want me to do? Find the probability that there are more than 30 survivors. 30 survivors. So now I gotta take that Poisson and convert it now into a normal distribution because the lambda is greater than 15. So now X, which is Poisson 20, can be converted into normal approximation gives me X, which is normal 2020. And what? And I'm trying to find the probability that X is that more than 30 survive. More than 30 survive. So we're looking for under this distribution the probability that X is greater than 30. If I apply continuity correction, It looks like I'm finding the probability that x is greater than 30.5, which is the same if I standardize. Probability that z is greater than 30.5 minus 20 over the root of 20. Probability that z is greater than 10.5 divided by, let's do that again, 2.348. Okay. Regular stuff, sketch. 2.348. Looking for that portion, that's 1 minus 5 of 2.348. Okay. Two point three four eight. 2.34.9904 plus 2.34, and I need 8. 8 is at 2. Okay, what are we looking at here? 1 minus 0.0094. Probability that x is greater than 30 is approximately that. .0094. Very good. Okay. That's the end of that problem. Let's try the next one. Yeah, this one is a bit quirky because clearly, if you define your new random variable at the beginning as the number of survivors out of 200 eggs laid, so your n, your number of trials is 200, your p-value, the probability that any one egg will survive is 0.1, that's clearly binomial. But they wanted us to show that it was Poisson, so effectively you converted the binomial to the Poisson. And then you took the Poisson and converted that to the normal distribution, which can be done, right? You're going in the right direction there. If you look back at the original chart that I gave you, binomial, and by the way, the only thing I didn't check was, and I'll do a quick mental check, NP that would have been 20, and NQ would have been 200 by 0.9, 180. So NP and NQ would have both been greater than 5, and therefore it was legit to convert the binomial to the Poisson. And of course, because this particular topic is dealing with the normal approximation to the Poisson, then you take that Poisson and you approximate it to the normal distribution and make your calculations. So let's move on. Okay, the next problem, this is an interesting one. When a trainee typist, they got trainee typists, types a document, the number of mistakes made on any one page is a Poisson variable, mean 3, independently of the number of mistakes made on any other page. Use tables or otherwise to find the 3 significant figures. The probability that the number of mistakes on the first page is less than 2. Okay, so it looks like we're using the Poisson as the Poisson here to begin with. Let's first define our random variable. X is a discrete random variable that represents the number of mistakes made by a trainee. typist per page of the document. Okay. And this is a Poisson variable with mean 3. So x is Poisson 3, which means the PDF would be probability x equal x would be e to the minus lambda times lambda to the x. Oops, what am I doing? I'm going to write my formula properly. E to the minus lambda times lambda to the power x upon x factorial. There. Okay. And first question, or the first part of the question is, find the probability that the number of mistakes on the first page, which is one page, is less than 2. So find the probability that x is less than 2, which is the same as the probability that x is equal to 0 plus the probability that x is equal to 1. That would be e to the minus 3 times 3 to the 0 upon 0 factorial. Actually factor the e to the minus 3 there. Plus 3 to the 0, 3 to the 1 upon 1 factorial. Let's try this again. E to the minus 3 into 3 to the 0 upon 0 factorial plus 3 to the 1 upon 1 factorial. That's 1, 3, 4. Times 4. 0.199. Yeah. 0.199. So the probability that x less than 2, what do you know? I think what I'll do, just go with a slight amount of space here. And I should have actually written the actual PDF, which is probability x equal x is equal to e to the minus 3 times 3 to the x upon x factorial. And that's what I plug into to get that stuff at the bottom there. Okay. All right, let's look at the next part of the question, which is the probability that the number of mistakes on the first page is more than 4. So now we're looking for the probability that x is greater than 4. There's no obvious maximum in a Poisson distribution. So therefore, I have to go 1 minus. Greater than 4 is equivalent to 1 minus the probability that x is less than or equal to 4. Okay, using the same PDF, this would be 1 minus into, I'll factor the e to the minus 3. And I'll go from 0 to 4. So 3 to the 0 upon 0 factorial, 3 to the 1 upon 1 factorial plus 3 squared upon 2 factorial, 3 cubed upon 3 factorial. 1 minus e to the minus 3 into, that's 1 plus 3 plus 9 halves plus 27, that's 9 halves again. 3, 3, 3, the 3 goes, so that's 9 halves, what do you know? 9 halves plus 9 halves is 18 halves, or 9. 10, 11, 12, 13. 1 minus e to the minus 3 times 13. Let's see how that works out. E times 13 equal 0.353. Probability that x is greater than 4, 0.353. Okay. Oh, I messed up that one. Is less than 2 is more than 4. More than 4, which is 5, going that way. So it's 4, 3, 2, 1, 0. Oh, what did I forget? I should have gone up to 4 on it. That's not far enough, my man. So this is plus 3 to the 4 upon 4 factorial. So that's 81 upon 24. All right. So that's 13. Plus 13. So the number in the bracket should have been 16.375. $16.375. Now let's check this out. Times e to the minus 3, and then 1 minus that. Yeah, this makes a lot more sense. 0.185. Okay, and then the last part. When the typist types a 48-page document, the total number of mistakes made by the typist is a Poisson variable with a mean of 144. Time to fire this typist. Bad joke. When no, it's not a bad joke. You type in a document with 144 with a 48-page document with 144 errors. Got to go. Okay. Use a suitable approximation. So first, I'm going to define my new random variable y, and I'll make sure I stick to y. What? Let y be a discrete random variable that represents give me a second here. Okay. Instead of duplicating this, I will copy and paste. There. Let y be a discrete random variable that represents the number of mistakes made by a trainee typist per 48 page document. Guess I still gotta write some of this stuff back. Per 48 page document. And if the number of errors per page is 3, my God. I'm sorry. Miss Typist, I'm assuming it's a girl. You're not cutting it. You made 144 errors in a document. How embarrassing. Look who talking. How much mistakes I is making these problems. I'm just ranting. That's why I represent the number of mistakes made in the training typist per 48 page document. If it's 3 per page, then lambda in this case is 144. My God. And y would be Poisson 144. This is a clear case in which you can make a normal approximation. If you make a normal approximation here, normal approximation will give you y being normal, lambda, 144, 144. And the question they're asking is, find the probability that the total number of mistakes is greater than 130. So we're looking for the probability that x is greater than 130. Continuity correction is required. You should know this stuff by heart by now. And therefore, this becomes the probability that x is greater than 130.5. Standardized, this becomes the probability that, you see I gone back to my x. Cha. Probability that y is greater than 130. Y is greater than 130.5. Standardized y, you get z is greater than 130.5 minus 144 divided by the root. Divided by 12. Minus 1.125. If I sketched, minus 1.125 greater than, by now this is standard fare, you should know this is the same as probability if you flip the graph that z is less than positive 1.125, which is phi of 1.125. 1.12.8686. And 1, 2, and then the 5. At 10. 0.0010. So that 1 will join the 8. And this becomes 0.8696. 8696. Yes, and if you round it off to three significant figures, it becomes 0.870. This represents the probability. That's a high probability, man. It represents the probability that y is greater than 1/30. And it's approximately equal because remember we made the Poisson to normal approximation. And that's the result there. Okay. I'll also give you a worksheet here. So again, exercise the page, and again, only 4 problems. It'll keep you busy and out of trouble as well. I'm gonna stop this video right here and jump straight into the other one that represents the Poisson approximation to the binomial. That's it for this one. I'm out.